Hello everyone, welcome back. If you are new, this is a new series that we have started in which we are trying to dissect segment trees from scratch. I already uploaded 5 videos in this series in which we have discussed the basics of segment trees, how to build segment trees, how to do point updates, range queries, the complexity analysis of each of these methods along with their proofs and the entire code walkthrough. After that, I said that before moving to range updates, we will strengthen our understanding of point updates and range queries itself. And I have given you a list of sample problems that can be solved using only point updates and range queries. And in the past few videos, we have been solving one variety of the problem wherein we are asked to query something on the prefix of the array. We have solved some problems of decent difficulty across various platforms, and we will continue solving the fifth problem from this list in this particular video. If you haven't watched any of the previous videos, I would link everything in the description down below. I would strongly encourage you to watch the entire series so that you can follow through the series by yourself. Basically, I asked you to pause the video and try to think several things by yourself. And if you have watched the entire series, then you can actually follow through and try and think some of the parts by yourself. So strongly encourage you to check out those videos as well. With that, let's get started. Before solving the fifth problem, which is how many LIS, we will first try to do a small quick recap of the previous problem, because that this problem is a prerequisite to solve the current problem, how many LIS. So the problem was we are given an array and we have to find out the longest length of the longest increasing subsequence, right? So in this case, the length of longest increasing subsequence is 3. So 169 is a longest increasing subsequence and its length is 3. So the answer here is 3, right? So how we have solved this? We said that, okay, we will try to find out the longest increasing subsequence at each index. So basically we'll say what is the length of longest increasing subsequence that ends at index 7, what is the length of longest increasing subsequence that ends at index 6, and so on and so forth. After we have figured out the length of longest increasing subsequence at each of the indexes, we will just take maximum over this result array and that would give us the final answer, right? Now, how to find the longest increasing subsequence that ends at a particular index is the question. So for that, we have come up with a n square algorithm wherein we are saying that, okay, for longest increasing subsequence that ends at index I, we will just iterate over all the indexes which are smaller than I and take the maximum over the result of those indexes if the value of the at that index is less than or greater than, if less than the current value of index I. Basically what we are saying is we want to find out the increasing subsequence that ends at 9, let's say, right? So what we can say is there the previous element of 9 would be some x, right? Now this x should be less than 9, right? Because this is strictly increasing subsequence, and the index of this x should also be less than the index of 9, right? So let's say the index of 9 is I. So index of j should also be less than I, because this is like a subsequence have to follow this condition. Now for each of these indexes, what you can say that, okay, if let's say the longest increasing subsequence length that ends at x is L, the longest increasing subsequence length that ends at 9 would just be L plus 1, right? So we will just iterate over all such possible x and take the one which give us the maximum value of L plus 1, right? And that's what we are doing here. We are iterating over all possible values or of j which lies before I, and only considering those elements which have the value smaller than the current index. And for all of them, we are taking a maximum over result j plus 1. right? Now again, this was just a quick recap. If you are not able to follow through this entire solution, I have uploaded the previous video in which I have gone through this entire solution step by step, starting from scratch. I would strongly encourage you to watch this video before moving ahead in this particular video so that you can get the complete understanding of the problem we are trying to solve in this particular video. So after we have figured out this, what we have said is we can just remove this inner loop with log n complexity by using segment tree. And how we will do that? Basically, this inner loop requires two conditions. We need to iterate over all the j which lies in the left of I, and the value of those should be smaller than the values of I, right? So to tackle this, but like we have tackled this exact same constraint in various problem in the series. So what we have done is we just tackle this particular constraint first by sorting the array. Now once we have sorted the array, each of these index would map to some index here, right? So 10 would map to this particular 10, 6 would map to something somewhere here, right? Now if we are asked to find iterate over all the indexes which are smaller than the current value, you can simply go to its mapped value and say, okay, I will iterate over everything in the left, because this array is sorted, everything in the left would be smaller than the current index, right? And after you have find out this, you have also to take care of the first condition, which is you only need to iterate over the indexes which are in the left of I. So for this, in this example, you can see 2 and 4 are also in the left of 6, but 2 and 4 in the actual array is in the right. So we don't have to consider 2 and 4 at all while iterating or while finding out some value for this particular index I. So to tackle that particular constraint, what we have said, we will iterate over the array from left to right, and we will keep on marking the elements which we have visited. So whenever we reach 6 or index I, we would have marked 1 and 3 only. And because 2 and 4 will not be marked, whatever operation we will do will only consider 1 and 3 and will not consider 2 and 4 at all. So just to conclude this with an example, let's say your current value, you are trying to find out the longest increasing subsequence that ends at 10. So what you will do, you will find out the mapping in the sorted array, and then you will say, okay, everything in the left is actually smaller than 10, but you only need to iterate over those elements which lies in the left of 10, and initially everything is 0. So 0 means that you haven't, like, these elements are not yet visited at all. So you will just do a range maximum over here. Range maximum would give you 0, and the value here would be 0 plus 1, which is 1, right? And before going to 8, you will also update the value in your segment tree as well, right? And you will keep on doing this, and finally you will get this array result populated, and you will just take the maximum over it, and that would be your answer. Again, any doubts in this particular approach, strongly encourage you to watch the previous video in this series which explained the entire concept from scratch, step by step. So with that, let's move on to the problem that we will be actually solving today, which is count LIS. In the previous problem, we just find out the length of the longest increasing subsequence. But here, we are asked to find out how many longest increasing subsequence exist. So for example, in this particular array, the longest increasing subsequence length is 3, right? And there are 5 different subsequence which have a length of 3. And those subsequence are 3, 4, 9, right? This is a subsequence which is strictly increasing and has length 3, which is the longest length possible. Similarly, 3, 6, 9 is another subsequence which have length 3 and is strictly increasing. Similarly, 1, 6, 9 is another one, 1, 4, 9 is another one, and 1, 2, 9 is another one. So there are these 5 sequences which have length of 3, and 3 is the longest increasing subsequence. So hence the answer here is 5. So you need to figure out this 5 uh, in this particular problem. Now, how to approach this? So again, we will try to solve this problem also in order n square first, and then we will see how to apply segment trees to reduce the complexity of the inner loop, right? So how to solve this in the n square? So with this loop, we are able to find out the long length of longest increasing subsequence by just iterating over all the indexes which are smaller than the current index and has value smaller than the current value. Now, can we do something similar for counting the number of number of largest increasing subsequence? Basically, let's say you already know the value of count of longest increasing subsequence for each of the previous indexes. So let's say for each of these indexes, you know the longest increasing subsequence and the count of longest increasing subsequence. Basically, this one here means that there is there is only one subsequence of length 2 possible that ends at this particular index j, right? So let's say you have this for all the indexes. Can you answer the value at index I with all these values? I would strongly encourage you to pause the video right away and try to think at least 10 minutes about this, about how you will actually find out the values at this particular index with the previous values. So hope you thought about it. Now notice that we we have to find the count of longest increasing subsequence, right? So before finding out the count, we have to first find out what is the length of longest increasing subsequence, right? Then only we will be able to find out how many of that particular length exist, right? So in this case again, we'll first find out LIS, which is 3 here. Now, why 3? Basically, we are following this exact same algorithm. We are iterating over every indexes which is smaller than 9 and lies in the left. So smaller than 9, like each of these value except 10 is smaller than 9 and lies in the left. So basically, we will take the maximum over each of these particular values, and if you take the maximum it will come out as 2, and the value here would be 2 plus 1, which is 3, right? Now once you have figured out the longest increasing subsequence, how exactly you will find out the count? So notice, you know that longest increasing subsequence is of length 3, right? Now let's talk about how many possibilities are there, like of the second character. So this is 9, right? The last one is 9. So let's see how many possibilities are there for second character. For second character, first possibility is 2, because 2 is smaller than 9 and has a largest increasing subsequence of length 2. Basically, you will not put 1 here. Why? Because if you put 1 here, you know that 1 has a longest increasing subsequence of 1. So you will not be able to fill this particular element at all. But what we want is, we want to figure out how many ways are there to fill these 3 indexes. So we know the last one will be 9. Now how many ways are there to fill these 2? So you will only consider those which have a longest increasing subsequence of 2, right? So in this case, we know that 2 is one of the probable candidate, right? Because 2 lies in the left and 2 is smaller than 9. Similarly, 4 is another probable candidate for the same reason, and finally 6 is another probable candidates for the same reason, because all 2, 4 and 6 have the longest increasing subsequence as 2, right? Now you know that there are two subsequence which can be possible with length 2 if the last element is 6. So basically what you're saying is, there are two such subsequences possible. So if there are two such subsequences possible, if you append 9 to each of them, you will get two more subsequences, right? Similarly, what we are saying here is there are two subsequences possible with 4. So there are two subsequences possible with 4. So you can just append 9 in each of them and you will get two more subsequence of length 3, right? And finally, we are saying that there is one subsequence of length 2 possible. So one subsequence of length 2 is possible. So we will just append 9 to that one particular subsequence and we will get one subsequence of length 3. So in total, there will be 5 subsequence of length 3 and hence 5 will be our answer. So this value would come out as 5, right? So hope you are able to follow through. Basically what we are doing is exactly similar trick. We first find out the longest increasing subsequence and after that we know what are the probable candidates for the previous element in the longest increasing subsequence race. So these are the three probable candidates here. Now for each of these candidates, we already know how many longest increasing subsequences can be possible, which ends at that particular index. And we can just sum them all up to get the number of longest increasing subsequence possible at the current index. Now, why we are summing them all up? Because we know that these are each of these are probable candidates. So if there are two possible ways or two possible subsequence that ends at 6, there will be two possible subsequences that ends at 9 and will be of length 3. And similarly for other cases. So we'll just sum them all up and we'll get the final result, right? So we are able to find out the value of a particular index I based on the value of previous indexes. So basically what that mean? This means we can simply modify this algorithm a little bit to get what we want. So this would be the pseudocode for this algorithm that we have just discussed. So we will first find out the longest increasing subsequence, right? So this loop is as is. We are finding out the LIS. Here I have just renamed the result array with LIS. Once we have find out LIS, we have to find out the count. So for count, what we will do, we will just iterate over only the ones. So it would initially be 0, right? So we'll iterate over only the ones which have this particular inequality satisfied. Basically, which we know that that particular element can be the second last element in the subsequence. So for each of them, we'll simply add the number of longest increasing subsequences that can end at that particular index. So with this, we are able to find out the count finally. But if you think about it, with segment tree, you can figure out this LIS. And after figuring out LIS, you need to then query something else, or like you have to do another range sum query over something else. So basically, if you go via this approach, you will be needing two segment trees, like one to figuring out LIS and second one to actually figuring out the sum of count, right? So to simplify these kind of constraint, always try to merge the for loops. So in this case, like it may not be possible in every scenario, but in this case, we can easily merge these two for loops. Again, I would encourage you to pause the video and try to merge these two for loops. This would be very straightforward, right? So what we are doing here, we are adding the count only when we know that the current index j is the maximum one, right? So we can simply do this on the fly. So what we can say is, while we are iterating over j, we will check if LIS of current index or whatever maximum known LIS that we have, if it is greater than the current index j plus 1, then we can simply continue because it means we are at an index which doesn't contribute the same LIS as other index would. So for example, let's say this is I and you are at index here, like j is at here. So in this case, you will see, okay, uh, the LIS of I is already 3, right? Because of these elements. So when you reach 3, you say that, okay, I can see the LIS here, maximum possible LIS here is 2. So because I already get 3, 2 is smaller, and we will just continue, right? So that's what we are doing. Otherwise, if we get to an element which is equals to the current LIS value, we will simply like sum their count, right? Otherwise, we will simply overwrite the LIS as well as the count, right? So this is just the standard way to merge these kind of for loops wherein you are finding out the maximum first and then you are trying to do something else over the maximum. So once we have this, we can simply use the single segment tree, and inside the single segment tree, the merge function would be having this logic. So basically, previously merge function have this maximum over result, right? But now merge function would be having this entire logic. So we'll look at the merge function of the segment tree again. But for now, this is the algorithm, and let's try to do a dry run over a sample. That would give you much more clarity. So let's just get rid of some of these stuff from here. Now again, we will be doing exact same thing which we have done in the LIS part. We will have two things. One is the result array and one is the sorted array. So previously we so the sorted array would be 1, 2, 3, 4, 6, 8, 9, 10. Right? Now this sorted array, we have two things, LIS and count, because we need both, right? Now what we will do again, let's start from 10. So we will go into the mapped position of 10. We know that all these elements are less than 10. We will simply do a range minimum over this element, and whatever value we will get, we will do a range sum over that element. So for currently everything is 0, so you will get 1 and 1 here, right? So what this means, it means that there is the longest possible longest increase in subsequence ending at index 0 is 1, and there is only one such subsequence which is of length 1, right? Similarly, like after do this, you will update the 10 as well, right? After that 8. So again for 8 you will go to the mapped position of 8, right? And say you will know, okay, all these elements are smaller than 8, so you will just do a range maximum over here, and whatever the value for the range maximum is, you will do a range sum over this. So currently everything again is 0, so it will come out as 0. So the length of longest increase subsequence is 1, and there is one possible subsequence, and you will update 8 here. The same fashion, 3 will also be 1 because everything before 3 is 0, right? So you will update 3 as well, right? And in the same fashion, 1 will also be updated to 1. Now after this, we got 6, right? So for 6, you know, this all elements are smaller than 6. So you will do a range maximum. Range maximum will give you 1. Now you will go in the second one and figure out the sum of all the elements which have the value 1, right? That's what you are doing here. So the value here would come as 2. So this would be 2 and this would be 2, right? So this would be 2 because the range maximum from the first array, which is the LIS array, was coming out as 1, and the LIS would be 1 plus 1, 2. And for the count, we will iterate over all the indexes which have the greatest value. The greatest value was 1, so we'll iterate over all these indexes and just do the sum over the counts. So sum of 1 plus 1, 2 is the value here. Now before moving forward, we'll update 2 here, right? And then For 4, again, what we will do, we will go over this. All these elements are smaller than 4, right? So we will figure out the range maximum over the first array. Range maximum is 1, and we will do a range sum over all the elements which have value 1 in the previous array. So here these two elements have value 1. So we will, the range sum would come as 2. So the value here would be 2 and the value here will be 2. So this 2 again comes from the first array. So before moving forward, we will update this to 4 to 2. And for 2, what we will do, we will do the same thing. We know everything in the left is smaller, so this is smaller. We will do a range maximum over the first one. We will get 1, so the value here will be 2. And then we will do the range sum over all the indexes which have value 1. So here there is only one index and the range sum would be 1. So the value here would be 1, right? And finally, before moving forward, you will update this here. And for 9, you will do a range maximum over this. Range maximum would give you 2. So the value here would be 3, right? And after that, you will do a range sum over here for all the indexes which have the value 2. So you will sum this, and this would come as 5, right? So hope this entire algorithm makes sense. Now, some of you might have doubt that, okay, we are doing range sum over some elements from the top. So we are considering some of the indexes, and these indexes can be non-contiguous as well. So in this case, as we have seen, we have taken this one and these two twos. So how exactly you will be able to tackle this in segment tree? So basically, this thing just boils down to writing out the merge function appropriately. So in this case, the merge function would look something like this. So let's just look at the merge function quickly, and then we'll look at the final code. So this would be segment tree. So basically each node, we are storing two things. One, the LIS, and second, the count of the LIS, right? So initially everything is 0, comma 1. Basically the length of LIS is 0 and number of such LIS is 1. So you can put it 1 or 0, nothing, doesn't matter much. So basically what we're saying is nothing is active. So length of longest increasing subsequence is 0 everywhere, right? Again, this is LIS and this is count, right? Now let's say you figure out the value for this particular index 10. The value is 1, comma 1. So for that, what you will do, you will update the last index to 1, comma 1, right? So let's do that. You will update this index to 1, comma 1. So this 0 would be translated to 1. Now what would happen? How will this change? Notice that you have to take summation over the maximum values only, right? So that's where what you will do, you will compare the left and the right. The left has value 0, the right has value 1. So because you have to take the maximum over, you have to take the summation over the maximum value, you will only consider the one which have the largest value. So in this case, the right one has the largest value over the left one. So you will completely ignore the left one and just override the current node value as the right node value. So right node value is 1, comma 1. So this would become 1, comma 1. Same goes for here. You know that you have to merge these two nodes. This node says that the longest increasing subsequence length is 1. This node says that longest increasing subsequence length is 0. You are only caring about the longest increasing subsequence length. And because 1 is greater than 0, you will simply override whatever is there in the left. So you will override it to 1. And in the same fashion, you will override this as well to 1, right? Now, let's say you got another query and you say that, okay, I will update this particular index to 1, right? Now, once you do this, how will this value change? Notice the maximum across the first value, which is the longest increasing subsequence, is 1. and both has the value 1. So the longest increase in subsequence is 1 across this entire range, and the number of such subsequence would be 2, because it says that left has one such subsequence and right has one such subsequence. So the longest increase in subsequence would be 2, summation of these two. Same fashion, when you will merge these two, you will say that okay, the longest increase in subsequence length in the left is 0, the longest increase in subsequence length in the right is 1. So you will, when you will merge, you will say okay, 1 is the largest one, so you will completely ignore the left one and just override this value with the right one. So the value here would be 1 comma 2. In the same fashion, this will also be updated to 1 comma 2. Now let's look at the last case again. Let's say you updated this to 3, right? 3 comma 5, let's say, right? So how will this change? Again, you will come here, you will say okay, what is the longest increasing subsequence across left and right? Left one has the longest increasing subsequence, which is 3. So you will simply override everything with 3 comma 5. Again, for this node, what will be the value? The longest increasing subsequence is 3, so you will update this to 3, and the value here would be 5, because there are 5 such subsequence of length 3, right? And right one doesn't have any subsequence of length 3, so right one doesn't contribute anything. And in the same fashion, this will be also be updated to 3 comma 5, right? So basically, you are writing your merge function in such a way that you are only considering the ones which have the largest value, and hence whenever you will query the segment tree for the sum, you will only be getting the values which are associated with the largest value here, right? So that's the way you will tackle figuring out the sum of the um, second array here, right? So let's look at the code. The code would make it very clear. Again, if you have followed through till this point, I would strongly encourage you to pause the video and try to code this entire solution by yourself. The only thing that would differ in this particular problem than the previous one is actually we it is the first time we are saving two different values in a single node, and we are modifying the merge function a little bit. Till now we have just seen that merge function is either taking the maximum or taking the sum or taking the minimum. The first time we have seen there is a custom merge function which actually captures what is the longest increasing subsequence and how many such subsequence exist in a given range, right? So let's look at the code again. You can submit this entire code in this particular Spoj problem, how many LIS. I would link that problem in the description down below, and you already have the sheet, so you can figure it out from that sheet as well. So this is the solution. Again, this is standard segment tree with just one exception, which is merge. We'll come to that merge afterwards. But for now, this entire thing is exactly similar to the one which we have discussed during the LIS. Basically, we are first figuring out this particular mapping, right? So we have sorted the array, and we have also maintained the indexes alongside, and finally we have said that okay, which position maps to which index here. So 10 maps to index 7, right? Similarly 8 maps to index 5, and so on and so forth. So this positions array would capture the actual mappings. After that, we have this segment tree, which we'll look at afterwards. And inside this, what we are doing, we are simply doing a lower bound. Again, why lower bound and why not just go to the mapped index? Because there can be multiple tens, right? And let's say you are at the second 10. So second 10 would map to this particular index, right? And during query you will say okay, find me the largest in this range, but that will not be the correct answer, because if you are not allowed to consider 10, because you are only allowed to consider the strictly increasing subsequences. So 10 doesn't count into strictly increasing subsequence. So you only have to consider up till 9. So that's where we are always doing a lower bound to figure out the first occurrence of that particular element. So once we have done lower bound, we know the first occurrence of this particular element. We will just do the query in the range 0 to, let's say this is LB, 0 to LB minus 1. So that's what we have done. If LB is greater than 0, we will simply do a query in 0 to LB minus 1, and whatever value we will get, we will simply increment the first one. So basically this will be a pair where first one would denote the length of longest increasing subsequence and second one would denote the count of such subsequences. So let's say the entire segment tree denotes the longest increase, the length is 5, right? So the 5 was the length without considering the current element, right, which is I. So after considering the current element, the length of the subsequence would become whatever length was there, L plus 1, right? So that's why we are incrementing the first value here because first value denote L. Second value will not be incremented because let's say there are 6 such subsequences which is of length 5. So there will be 6 subsequences only which will be of length 6, right? So that's why we have only incremented the first value, and this is just to take care of the modulus. After we have figured out the value, we will just update that particular position in the tree, and after we have completed this entire loop, what we will have this particular array built out, and we can simply go over this array and get the maximum. So here the maximum is 3, so we will just return 3 comma 5 as a result. So we are just getting the query in 0 to n minus 1. Now coming to segment tree, this part is standard, which we have in other solution as well. In update, what we are doing, we this is just a point update, so we just check if the index we need to update lies in the left or the right. Accordingly, we'll go either in the left or in the right. After we have gone in the left or right, we will merge left and right because let's say you have updated this particular node. So once you have updated this particular node, this node may also change. So that's why we are updating this node as well by just merging this node and this node again. So we simply call merge function here on left and right. And in the same way for query, what we are doing, we are simply iterating like this is the basic query formula, right? We will see if the range is completely outside of the current range x comma y. If it is outside, we will return a neutralizer value. So in case of minimum it was int max, in case of maximum it was int min. Here it is 0 comma 1 because 0 comma 1 says that the longest increasing subsequence is of length 0, and we know that the longest increasing subsequence will always be greater than length 0, and hence this 0 comma 1, whenever we take maximum of 0 comma 1 with any of these nodes, the value would be the other node. So maximum of 0 comma 1 and let's say 1 comma 1, the value would be 1 comma 1. Similarly, maximum of 0 comma 1 or 3 comma 5, maximum would be 3 comma 5 itself, right? So this 0 comma 1 is the neutralizer value here, and if the range is completely overlapping, we'll just return the current value. Otherwise, we'll simply merge the queries from the left and the right part. Now merge function is again very similar. We will look at if the values are equal, then we will sum their right hand side, right? So this merge function is exactly similar to this particular part. What we are saying is if they are equal, we will merge their right hand side. If they are not equal, we will completely override. So if they are equal, we are merging their right hand side. If they are not equal, we are completely overriding, basically taking whichever is the maximum. Now One small case is the value of 0, because basically we need to take care that whenever there is 0, we always return 0 comma 1, because that's the default value, right? So hope this entire solution makes sense. The complexity is still order n log n, because we are doing lower bound here and a tree dot query and tree dot update, which is of log n. So we are doing 3 log n operations inside a loop which runs n times. So entire complexity is still order n log n. So hope this entire solution makes sense. If you have any doubts in this particular problem, feel free to post them in the comment section below. If you are unclear about any of the particular section of the solution, I would include the timestamp of each and every part in the description below. You can watch back and forth. You can go back and forth in the video and try to watch a specific section that you think you are not completely sure of. With that, uh, if you like the video, give it a thumbs up and do subscribe if you haven't already. And I will see you in the next one. Thank you.